record. Yes, good. Okay, so today we are summarizing this course. I'm trying to figure out what is the important things. Let's note that you are allowed to make personal notes that you can bring to the exam. I think it was Elizabeth who asked for this, and I've done this in Tromsø, and I think and then I decided, yes, we can do that. Is it good? I think I usually try to make the exam so that you don't need to recall too much details. Of course, you have to have an overall understanding of the principles, but I don't really like people to have to recall all sorts of details. But I think preparing such a note, personal note on the course is a good preparation. So I think it's a good thing to allow because it's a good preparation for the course. Yes. Let's see. Okay, so summary. Please interrupt me and ask if there are things you want me to discuss further. Summary. Mat220 spring 2026. In brief, what is the curriculum here? It is the curriculum. It's all chapters 1 to 8. That's a basic core material about fields and rings and quotients and groups and all that. So that's chapter 1 to chapter 8. Everything except chapter 8.5. All except chapter 8.5. That's the proof that A5 is simple, which we didn't do. So that's a core material. And then there is chapter 9. In chapter 9, we only did 9.1 and 9.2, which is about finite abelian groups. Classification of finite abelian groups. And then we did chapter 10.4, which is about the so-called field of quotients. Of integral domains. So that's a construction. I think it's just a construction. It just shows that the way we usually go from the integers to the fractions, to the rationals, can be generalized to any integral domain. You can start with things like f of x polynomials with coefficients in the field, and go to the rational functions with the polynomials divided by polynomials. So 10.4 is a construction. So it's just to see that this is a general construction. Chapter 11. In chapter 11, we only have 11.6 as our curriculum. 11.6 was the classification of finite fields. I will return to it, but the main result is that there is one finite field for any power of a prime, and that's the field with the number of elements being p to the n. It's called the Galois field of p to the n elements. Classification of finite fields, that's what we did in 11. There was also 11.1 to 11.5 that I flipped through a little bit, but that was mostly to be able to complete the proof of this classification. But the main thing is to understand the classification of finite fields and how they're constructed. And then it was chapter 14, which was 14.1 and 14.2, not 14.3. I think that was this Chinese remainder thing, yes, except for the more general situation of rings. Yeah, that was Chinese remainder theorem, CRT, which is very close to chapter 9. So chapter 9 and chapter 14 are essentially the same thing. And then there was chapter 15, geometric constructions. Really what to do there if I want to ask something. I don't know. I think it's not so easy to ask. But I don't know really how one can ask proper questions about this, but I think it was a nice application showing that this algebra and these field extensions could be used to study something that is classical mathematics. And then there was two notes. There was this note about Euclidean, the extended Euclidean algorithm. And there is a note on shift registers. Yeah. Perhaps we return to look at what I really want you to know from these two. The shift register note has more information than I really want you to recall. There was a question here. Well, I return to this shift register thing in the end, but okay. Yes, so let's start to discuss what I really think you should focus on to understand the structure of these things. I find this Wikipedia classification of algebraic structures has been quite useful. So what structures have we done in this course in 220? First of all, there's this chapters 8 and 9, which is about groups. So we have I'll return to those afterwards, but that everything related to groups is several of these structures. And then apart from groups, there are rings. And for rings, I find useful this Wikipedia classification saying that a ring with identity is a commutative ring. No, opposite. A commutative ring is a ring. So towards left, this is a relation. Commutative ring. With identity. Integral domain. So that's GCD domain. I don't think we define it very precisely, but it's a domain where you can do where you can compute greatest common devices.
Couldn't you put like field in between the integral domain and the commutative ring?
No, the field comes later. The field is sort of the bottom of this chain. So the field has every other property. Integral domain, GCD domain, and then the next one is I skipped a few of them because that's not things we've discussed. Into GCD domain, unique factorization.
Is the GCD domain the same as a Euclidean domain, or is it?
For us, yes, it's the same, but it is not the same. You could imagine there exists GCD domains that doesn't have a Euclidean algorithm. It exists, but I don't think we have seen it at all. So for us, these collapse some of these things. Unique factorization, GCD. So you could have a GCD without having unique factorization, but it's very esoteric. So some of these inclusions towards the right here are to us essential identities. But it is useful because it says the structure of how you can prove things, what you need to prove things. So then you have unique factorization domains, and then you have principal ideal domains. And then you have Euclidean domain, where you have some notion of Euclidean algorithm division. And then you have fields. Now you have fields. Fields have everything. But fields as Euclidean domains is very simple because you always get zero in remainder when you divide in a field. So the Euclidean division in a field is trivial. Things collapse there a bit. And then you have algebraically closed fields, where you can solve all polynomial equations. But I think for this to make sense, you need to know what are these things. This is quite important. Let's just yeah. So ring we know, but the book is actually quite odd in this respect of defining rings. They define a ring as something that doesn't necessarily have an identity element. Usually in modern algebra texts, they say a ring is a structure with the identity element. That's the modern definition. The book says that everything that has a plus multiplication satisfying these rules is a ring, even if it doesn't have an identity. What does it mean? It means that in the book they would call an ideal ring, a subring. In other algebra texts, they would not call an ideal a subring. They would say it is a linear subspace that has an absorbing property with respect to multiplication. That's an ideal in a modern text. And such a thing that has a linear structure and a multiplication rule, it's just like a vector space over the base ring. That is called a module. So in the modern text, they would say that an ideal is a module. In this book, they say an ideal is a ring without an identity, necessarily not with an identity. It's not so important except when you want to discuss morphisms between these spaces. Then there's some issues there. But that's not an important detail. Okay, let's just see what are these things. Integral domain. What is integral domain? What is an integral domain?
No zero divisors.
It's commutative ring, yes. So with identity, yes. Cool.
It's not the same as the zero.
And identity is not the same as zero. Yeah, that is more subtle things there. Commutative ring with identity, no zero divisors. And one is different from zero. Yeah, this is integral domain. GCD, I just think of GCD domain as a domain where we have a GCD algorithm. So it comes from Euclidean domain. For me, essentially all this is the same, even if they're not. And that's the way the book is also building up things. They start with discussing about the integers, which is the Euclidean domain. You have Euclidean division in the integers, and then in chapter 1 they start by doing GCD algorithm, and they show unique factorization. This principal ideal domain, that's something that probably has not been discussed so carefully in our course, but it's an important notion. What is a principal PID? What is it? Do you know what is a PID?
Idealist principle.
Yeah. So it's again, it's a commutative ring with unity, and Of course, it has no zero divisors since it is an integral domain. But the important thing is that it is a commutative ring with 1, and 1 is different from 0, and it has no zero divisors. But the important thing is that every ideal is principal, generated by one element. So that means that if I do something like the ideal generated by two polynomials, then it can always be generated by one polynomial. So any ideal can be its principal can be generated by a single element. Why does this follow from the Euclidean algorithm? I think it's useful that since we are doing this now at this point, I think we can discuss why does it have the property that if you have the Euclidean algorithm, you can always generate everything from a single element. So it's like this. Assume that we have a Euclidean domain. If I have a Euclidean domain, so I have Euclidean algorithm, and I want to be a bit more specific. I want to do an example. I want to do polynomials where f is a field. If I have polynomials where the coefficients are from a field, then it is a Euclidean domain. Then I have a Euclidean division algorithm. If the coefficients of the polynomials is not from a field, then I do not have necessarily a Euclidean algorithm. Okay, so now let's say that I have an ideal, and I let f inside the ideal be the polynomial of lowest degree. That's the trick. You pick from the ideal, you pick the polynomial in the ideal that has the lowest degree. And the result is that the ideal is generated by this f. So if you have an ideal and you have an Euclidean algorithm, you can always replace any generator by the polynomial of lowest degree. And the trick is just by doing the Euclidean division. If I have a g in the ideal, the polynomial g, what do? I say that g of x is f of x times q of x plus r of x. And then I say that, yes, this is in the ideal. This is in the ideal. This is a product of something in the ideal. So this is in the ideal. This is in the ideal. So then this is in the ideal. If this and this are in the ideal, then R is in the ideal. So that's, now we have R in the ideal. But the degree of R, oh, we have two possibilities. Either R is 0 or the degree of R is smaller than the degree of F. Degree of F is the smallest. F was the one that had the lowest degree, smallest degree. So this is not possible. It cannot have lower degree than F, so it must be 0. So the remainder is 0. So this is 0. R is 0, and then we see that yes, and then we see that G can be generated by F. F times Q. So anything can be generated by so that's the point. And this is quite useful many times to know that something is a principal ideal, because then things become rather simple. I will return to that. Yes, so we have a principal ideal domain, then we have a Euclidean algorithm. We have fields which has everything. That's just a commutative ring with 0 being different from 1, and all non-zero elements are units. And then you have algebraically closed fields that we can get by field extensions from this one.
But field did not always have the zero divisors, right? The non-zero divisors.
It has no field has never any. What was your question? If they have any zero divisors,
Yeah.
a field has never any zero divisors. But also an integral domain has no zero divisors. So a field is very much special. It has a property that not only does it have no zero divisors, but it's all non-zero elements are invertible. That's the main issue. And those elements that are invertible, they cannot be zero divisors.
Okay.
Yeah. So if every non-zero element is invertible, it follows that it has no zero divisors. Yes. But the zero divisor, something that is not a zero divisor, doesn't need to be invertible. For instance, you are in the integers. You have no zero divisors, but you cannot invert 4 or 5. The only element you can invert in the integers is 1. 1 divided by 1 is 1. So the integers has no except for 1, it has no other invertible elements. The one is
-1 is also
-1, sorry. Yeah, 1 and -1. It's the same with polynomials over f, where f is a field. Because they are exactly so if f is a field, then polynomials over a field is a Euclidean domain. So it is an integral domain. So it has it has no zero divisors, but it doesn't mean that every polynomial can be inverted. Yeah, exactly. Okay, let's now try to go through the different chapters and see how we did build up all these structures really gradually in the course. It's not so obvious at first reading that this is the structure of the book, but it is essentially for a lot of the things going on in the beginning. It starts with chapter 1, arithmetic in Z. Yes. And it starts by the Euclidean algorithm. Then it discusses GCD. Then we develop the theory of unique factorization. So that's essentially what is going on in chapter 1. On the way, we do various things that turn out to be very useful later. In the GCD, we get the Bezout theorem saying that if D is the GCD of A and B, then we have U and V, such that A U plus B V equals D. Bezout. We had this meeting. There was this women in mathematics meeting. None of you were there because you didn't see the invitation. Is that so? It was a film about Sophie Germain last Friday. Okay, sorry. But there was some people. There was something in this film. Some people mentioning Bezout. I really don't know about Bezout, who he was, but early 18th, 19th century, everything. Unique factorization. And then you have characterizations of primes and primes. Yeah. So and there are some ways of getting to primes. So unique factorization. So P prime. The only, I think that's the way they define it, the only factors are the units, which in this case of Z is plus minus 1, and P itself, or and the unit times P, of course. So plus or minus P. This is a prime defined like this in the book, and that's how it goes also when you come to polynomials. Polynomial is has this prime property if the only, it's irreducible if the only factors are the units and P itself. But the other characterization is this one. Prime or irreducible. The other one is that the characterization is this one, that if P divides a product, then P divides one of the factors. There are some subtleties here because when we do this in the beginning, it looks like these things are exactly the same. They're not completely equivalent, these things, having this irreducible property that the only factors are the units and P itself, or the fact that you have this this ideal. This was really what we used when we defined prime ideals, this property that if it divides a product, then it divides one of the factors. That's P is a prime if and only if it has this property. There are some subtleties about these things. I'm not sure if this is really so important to stress, but let's just summarize it. And this is kind of things I have to admit, this is something I have to ask ChatGPT to get this correct, because I don't. So it's not so important really, but irreducible versus prime. Let's just do it. Irreducible versus prime. Irreducible for polynomials and so on would be that if P is A times B, then A or B is a unit, an invertible element. So in the case of integers, plus or minus 1. Whenever you can factor it, one of the factors is a unit. That's irreducible for polynomials. Prime, the property of being prime, when you ask about polynomials and so on, prime ideals, prime things, is the fact that if P divides the product, then P divides A or P divides P. Are these equivalent, these two conditions? Not completely. It is actually so that if you have this prime property, it implies always that it is irreducible. The opposite way, if you have something that is irreducible, it implies being prime in unique factorization domains. So in unique factor, if you have unique factorization, then this property of being prime is the same as being irreducible. So for instance, so what are typical unique factorization domains? back to our list, unique factorization is, where's unique factorization? Here's unique factorization. All these principal ideal elements, everything where you have a Euclidean algorithm and so on, that's unique factorization. So for us, the important unique factorization domains are the integers and f of x polynomials where f is a field. In these cases, the two conditions are equivalent. If you talk about irreducible elements, that's those that has only the only factor is a unit, or having this prime property that if it divides a product, then it divides one of the factors. This is the same if you have unique factorization. So for us, in the case of polynomials over a field and integers. Okay, so that's let's go back to our chapter 1. So chapter 1 is doing these basic things, building up things, GCD algorithm, unique factorization, and so on, and ending up with the unique factorization. This is the fundamental theorem of arithmetic, saying that any number can be factored in prime numbers where the factorization is essentially unique. So that holds for any any of these cases where you have a Euclidean algorithm, then you have unique factorization. Okay, chapter 2. And please stop me if you want to discuss something more. Chapter 2. Chapter 2 is congruence and modular arithmetic. I would say this is a chapter where you should be able, have to be able to ask some questions that you can compute arithmetic. So you must be able to do some basic computations. Okay, the chapter starts by defining. Actually, there is an important start of this chapter because it starts by discussing equivalence relations. And an equivalence relation is something like this. M is equivalent to N mod K if M minus N equals K times L for some L. So this is an example of an equivalence relation, and an important thing, and that is going on all the time in this course. Equivalence relation has three properties. It is symmetric, transitive, and reflexive, symmetric, and transitive. And it always defines partition of the domain into equivalent parts. And the important question, so reflexive, so one of them is that x is equivalent to x. The other one is that x equivalent to y implies y equivalent to x. The third one is that x equivalent to y equivalent to z. That's a transitive one. X equivalent to z. That's the things. This is very important because that's the basis for all kind of quotient constructions, that you get the domain divided into congruence classes, and we always have this basic thing that we have to check that you have an algebraic structure, you have an equivalence relation, you divide out by the equivalence relation, and that you have to check that the operations are well defined on the equivalence classes, that it doesn't matter which element you pick from the equivalence classes. So operations plus and times in this example. are well defined on equivalence classes. So in that case, you have this quotient. NZ is an all okay if it is mod K. K is K set, K mod K. This we call ZK. That's the equivalence classes mod K. Mod K. I think at this point, it is useful to recall, jump to a much later chapter, but it's useful at this point to recall what is called the first isomorphism theorem. Because there are two ways to consider such a quotient. There are two ways. Either you consider it to something constructed explicitly by saying, okay, it's numbers from 0 to k minus 1 with additional multiplication mod k. That's this view. Or you consider it as equivalence classes upstairs. And in that case, you have to think of it as equivalence classes. And the basic first isomorphism theorem says essentially that if you have Z and you have this concrete ZK, let's say ZK is concretely the number 0 up to k minus 1 plus and multiplication mod k. Then if you have a homomorphism between two rings like that, ring homomorphism, in general it's like this. I have a G and I have a K. Ring homomorphism. Then we consider the kernel of the homomorphism, and we consider the image. So the first isomorphism theorem says that the kernel of phi inside G is an ideal. And the other part says that the image of phi inside K is a subring, sub blah blah, depending on what structure you're talking about, subring in the case of rings. The image is an ideal or a normal subgroup. The kernel is an ideal or normal subgroup. The image is a subring or a subgroup in the group theory. And the final statement is that if you take G and divide it by this ideal defined by this kernel, then this is also naturally isomorphic to the no, sorry. If you take G and divide out by the kernel of phi, then you get something that is isomorphic to the image of phi. In particular, as is the case here, if phi is surjective, it maps to everything, then the image is the same as this one. So in this case, we would have that ZK is isomorphic to Z over the kernel of phi. So, and in this case, what is phi? Phi is mod phi of x, phi of n. Phi of n is defined to be n mod k in this case. So what is the kernel of this one? That's kernel of phi is just all multiples of n, nc, or the same as we also write as n, the ideal generated by n. So by k, sorry. So zk is essentially the same as z divided by k. But this first isomorphism theorem says that this is really something that is two views of the same thing, that you could either consider it to be equivalence classes of equivalence relation, or you can consider it to be something that you construct more explicitly as a thing. Okay, I think we take a break. Yeah, we take a break. Yes. Men jeg har ikke hørt fra Elisabeth. Er du der fortsatt, Elisabeth? Ja, ok. Sånn er det.
Ja.
Så du har ikke noe spørsmål? Jeg har ikke hørt noe fra deg.
Jeg sitter og noterer. Jeg synes dette er veldig vanskelig, men det er veldig fint å få en oversikt over hva som du vektlegger.
Ja, ok. Hvor er du?
I Farsund.
Hva sa du?
I Farsund.
I Farsund, ja. Så jeg har jo ikke hatt mye kontakt med de som tar dette. Jeg ble liksom bare fikk beskjed om at det var noen som skulle ta det som sånn ekstra, som dette selvstudiumskurset. Så jeg har jo dessverre ikke hatt mye kontakt med dere, da, men ok. Fint.
Neida, men sånn er det.
Ja.
Hvor lenge tenker du har pause?
Yes. So we are, what are we doing? We have been discussing chapter 2, congruence and modular arithmetic. What should you know? You have to know things like theorem 2.8 to 2.10, which is basic things about solving congruences. There are various results here, but you have to know these things. If P is a prime. If you look at this Zn, then Zn is a field if and only if n is a prime. This is a basic thing. The only of these that are fields are those where P is a prime. And then you have things like units that ax equals 1 as solution in Zn if and only if GCD of n and a and or x, not n and a. X is what you want to as solution. X is equal to 1. If a is relative prime to n, then it has solution. Otherwise, it does not have a solution. That's the units. That's the units are those that have a relative prime to n. And then all the others are zero divisors. So zero divisors. Zero divisors are those where you can solve a x equals 0 for a different from 0 and x different from 0. And a is zero divisor if and only if GCD of a and n is different from 1. Different from 1. That was ugly. Sorry. GCD of A and N is different from 1. For instance, if you're in Z12, then you have 1, 5, 7, 11 are units in what we call Z12 cross, like that. That's a group of units. While all the others, 2, 2, 3, 4, 6, 8, 9, 10 are zero divisors. For instance, if you take 8 times, what should you multiply by? 8 times something, then you get 0. 8 times 3? No, 4?
Yes, it's
No, you have to multiply by 6 or something, by 3. If you multiply by 3, then you get something that contains 12, yes. It contains 12 is 4 times 3. That's the point. 8 already has the factors 4. So if I multiply by 3, then I get 24, which is congruent to 0. So 8 is a zero divisor. 3 is a zero divisor. Yes, so that's the example. So, units and zero divisors, and of course you have to be able to compute the Bezout number so that you can find the inverse. So if I have AU plus NV equals 1, if GCD of A and N is equal to 1, and I want to solve AX equals 1, then I compute the Bezout numbers U and V, and then U is AU is congruent to 1 mod N. So A inverse is this U. You have to be able to compute this. That's definitely so. I think that's essential thing of chapter 2, that it's this kind of basic modular arithmetic, and you should be able to do some basic computations of this kind. Chapter 3 starts with rings. So rings, units, cancellation. It's very basic things. So I don't think we need to really go through it because it comes back later also. But it's a basic notions of subring units, zero divisors. Zero divisors is a bit subtle. If you think about non-commutative rings, then you could have zero divisors from one side and not from the other side and so on. But we have not really discussed non-commutative rings, so I would say I'm not going to ask you about non-commutative rings. Non-commutative rings is not pensum, such as rings of matrices and so on. We are not doing it. But if you are in non-commutative setting like products of matrices and so on, you could have something that is a zero divisor from the left, but not from the right and so on. So but it's not so for us. We haven't done it. Units. Zero
Sorry?
divisors. Yes, sorry.
Can you say that you said now about the matrix one more time? So non-commutative rings is not tensor.
So non-commutative rings are example of non-commutative rings could be something like R n times n all square matrices. That's a non-commutative ring where you have the product is a matrix product, and then you have sums of matrices. We have not really discussed this kind of examples. The important here is, of course, that A times B is not the same as B times A. So that's a basic fact of a non-commutative ring, that the product is not commutative like in matrices. And in that case, you can have a bit more subtle things about zero divisors. You could have something like could probably have matrices like I don't recall the examples, but something like triangular matrices that have zero divisors from one side but not from the other side, and so on. But my statement is just that just forget about non-commutative rings. All the rings we will discuss in this course are commutative rings. So all this is a big parenthesis. Yeah. We're not doing a non-commutative ring theory in this course. We have not discussed it. Zero divisors, yes. And these are not the same. I mean, you have zero divisors, and if you have no zero divisors, then you can always cancel. You don't need inverse. You don't need. Okay, units must be cannot be units cannot be zero divisors, but zero divisors do not need to be units. So if you are in an integral domain, you have no like Z, you have no zero divisors. You have quite a lot of you don't have many units, but whenever you have something like A C equals B C, you can cancel A equals B. You can cancel, and okay, there's a left and right issue here also, but I'm saying that everything is commutative, so then it doesn't matter about left and right. But this is a cancellation law, and cancellation, to do cancellation, all you need is that there are not zero divisors. Why is that? Because if you have AC equals BC, then you have A minus B, C equals 0. And if you have no zero divisors, then you have that A minus B.
I think you need to require that C is non-zero as well.
Because
Yes, you have to require, yeah, exactly. Okay, that's the point. Yeah. You have a cancellation if C is different from 0, of course, yes. Yes, thank you. If C is different from 0, then you have cancellation. And because you move over like that, and then A minus C is 0, which we have excluded, or A minus B is 0. So that's because we have no zero divisors, then this must be 0, which means that A equals B. Yeah. So zero divisors allow you to do cancellation. No zero divisors allow you to do cancellation. That's the basic thing. That's chapter 2. Chapter 3. Chapter 4 is now about polynomials. Now we start to get into two things. We are considering things like f of x, where f is a field. Well, we could also consider r of x, where r is a ring. The special thing about fields is that if f is a field, then f of x is a Euclidean domain and all that. and is also an integral domain in particular. So when you take polynomials and your coefficients are from a field, and then you are in a very nice algebraic situation. If you take polynomials with coefficients that are not there, it's more complicated. So we talked about a little bit about this prime. Yeah, let's come back to that later when we talk about ideals. Yeah. But it means that if you are in a field, then you have a Euclidean division. You have GCD, you have unique factorization domain, you have no zero divisors, etc., etc. It's in this case everything is extremely nice, and you can compute also the field of. You can extend it is an integral domain, and you can extend it to rational functions, which is the field of rationals. Functions, as we did in chapter 10 something. Okay, that's chapter 4. Perhaps a bit messy. I'm now. Yes. I think it's appropriate at this point to look ahead a bit towards the chapter much later on ideals. So I think we jump now and talk a little bit about ideals. Recall ideals later. We have that. We have the two basic ideas, basic special classes of ideals. So we have an ideal inside a ring, commutative ring. Let's say with unity, I think we have a commutative ring with unity, and I have an ideal. And the basic thing is that an ideal is something inside which is a linear subspace. If I add two things in an ideal, I stay in the ideal, and it's absorbing with respect to multiplication, absorbing multiplication. So if I is in the ideal, then I times A is in the ideal for all A in the ring. Anything in the ring multiplied by something in the ideal stays in the ideal. That's an ideal. And then you have the basic types of ideals, which is prime ideals. Prime. An ideal is prime if an ideal is prime if A times B inside the ideal implies that A is in the ideal or B is in the ideal. That's a prime ideal. And then we have the maximal ideal.
I think also you have to require that I is not equal to R.
Yes, it's a proper, thank you. So a prime ideal is a proper ideal with this property. So I write it like this. It's included, but it's not the whole thing. Yeah, that's a prime ideal. And then we have a max ideal. Max ideal is something which has nothing between properly between the ideal. So again, it's an ideal which is not R, such that there is nothing in between. If J is between R and I, then J equals I, or J equals R. That's maximal ideal. And then the basic structure things about prime and maximal ideals is the following. R divided by an ideal is a field if and only if the ideal is maximal. R divided by an ideal is an integral domain if and only if I is prime. What do we get out of this? We get immediately that any maximal ideal is prime. Yes? Max implies prime always. Because if it's maximal, then this is a field. The field is in particular an integral domain. The field is an integral domain, and therefore it is prime. Yes. So any maximal ideal is prime. The other way around, it's not always true. But it is true in the case of things like polynomials over f. So f of x, that's why I took it now. What about f of x? This is a Euclidean domain, so it is actually the story is just like this. It's Euclidean domain, so it's a principal ideal domain, and in the principal ideal domain, any prime ideal is also maximal. But why is it so? Because if an ideal is prime, so I have an ideal inside here. I prime implies that and f of x is Euclidean domain. It implies that if it's prime and the domain is a principal, so f of x is a PID, and then prime implies maximal. So for this kind of examples, which we are doing a lot of this kind of examples. We're doing z and f of x, the f is a field. In these cases, prime and maximal is the same. It's no difference. So to find examples where prime and maximal are different, then you have to do something else. So examples where prime is not the same as max. I think the standard example is z of x, which is polynomials with integer coefficients. In this case, you can find things that are, it's not Euclidean domain. You don't have, it's not principal ideal domain. You could have things that are generated by several elements that are not generated by one element, and you could have examples of things that are maximal and not prime. That are prime but not maximal. Maximal implies prime but not the other way around. So you could have the ideal I1 being generated by 2. You could have the ideal I2 generated by X. And you can have the ideal I3 generated by 2 and X. And you can discuss various of these examples. Where is what is the quotient? Is it field or is it integral domain? Are these things maximal or prime? And then you will see that they are not the same. There was an exercise. Look at this exercise we did a while ago. Exercise. How was it? This one? The ideal generated by 2, that's everything you get by multiplying by 2. So that's all the polynomials with even coefficients. So I1 is polynomial with even coefficients. I2 is that's polynomials with 0 constant terms. That's everything that is multiplied by x. So it's pol with 0 constant term. And I3 are polynomials with even coefficients and 0 constant terms. And what is z of x divided by I1? So you take. Oh, now I'm really. How is this? What is z divided by I1? You take all polynomials and you divide that by those who have even coefficients.
Would it be something like if every coefficient
I guess it should be, isn't it C2? You get just 2 equivalence classes. You get those that have even coefficients.
I would think it would be if you have 2 polynomials and the sort of type of each coefficient is the same, right? Or
At the moment, this is more. It was clear to me at the point, but now it's not so clear. Okay, you take all polynomials with. Okay, let's just say. Okay, well, if you take z of x and divide by. If you take z of x and divide that by I2, then you say that all polynomials are equivalent if they have the same constant term. So this is the same as z itself. This is z. That's just you're left only with the constant term because you divide out everything that has higher powers in x. All these things that have higher powers in x, you divide out, and you get this, which is so this ideal here is prime, but it's not maximal because you have something that is an integral domain, but it's not a field. So I2 is prime, not max. Yeah, that's an example. That's something that is prime, not maximum. I think we stopped this example here, but we had such an example in one of the exercise classes. But to find examples of things that are prime but not maximal, you have to go to cases where you don't have the Euclidean division, like in this case. Yeah. Okay. Sorry. Yeah. So chapter 4.3. We are running out of time. 4.3 is about irreducibles and unique factorization. We already discussed this. This is about prime ideals and irreducible and so on. So no, that's 4.3 is a discussion about irreducible and unique factorization. I think we have discussed it already, these things, because I've looked ahead. And then you have 4.4 about polynomial functions and roots and reducibility. Polynomial functions. What is basic here is theorem 4.16, which says that I have an f of x inside a polynomial with coefficients in the field. And then a basic thing is that if I want to compute, polynomial functions, this is the point, that polynomials and polynomial functions are different. Polynomial functions is when you really put the value in for the x, and it's not the same as the polynomial itself with x is just a non-determined entity. F of a is always the same as in this case when I'm in a polynomial with coefficients from the field, then I have that f of a polynomial function is just the same as taking f of x, the polynomial, and divide out by, and take the moduli with respect to the division remainder of x minus a. So this is a basic thing that you can evaluate the polynomial by dividing and looking at the division remainder, or vice versa. If you want to compute the division remainder, you can take the evaluation of the function in A. And then we get to eventually to all these unique factorizations on polynomials. So again, I think this chapter 4 is a bit of a repetition of chapter 1, but it's essentially doing the same exercise as we did in chapter 1 to go up like this. You start by saying if you have f of x, then you are in a Euclidean case. You have a unique factorization, you have GCD and so on, and this is what is done in chapter 4. And then comes chapter 4.5, which is practical ways of determining whether polynomials are reducible or not. That's irreducibility in Q of x. I have polynomials with, let's seek roots within the rational numbers. So there are two basic theorems that we worked a lot to establish, and that was theorem 421. And these things are useful because they come back when we discuss this geometric constructions and so on. 421 is the rational root test. And the point is that if I have I'm considering polynomials in Q of x, then I can always scale them up so that the coefficients are integer coefficients. I can always scale up and get integer coefficients. So I can always look at that. And if I have an f of x, being an x to the n plus a0, where ai are integers. And I consider f of x to be a polynomial in q of x, meaning that my roots will be considered as rational functions. And then if alpha is a root, is r over s, is a root. Then the rational root test says that the numerator must divide a0, and the denominator must divide an. This gives quite a lot of restrictions on the possibility, possible roots of a polynomial with the integer coefficients. And you can quite easily check all possibilities in many cases, and then you can check if it has any rational roots by this test. That's quite useful as a way to check if and then the famous one is the Eisenstein criterion. It's more complicated. That's 424. We worked quite a lot to get that one. That's Eisenstein. Again, we have a polynomial where we look for rational roots. And we have scaled it up so that f of x is equal to an x to the n plus a0, where all coefficients are now scaled up to be integers. And then Eisenstein says that if p is a prime, and if p divides all the coefficients except the highest one, p divides a0, p divides a1, p divides an minus 1, but p does not divide an. So I have a prime that divides all the coefficients except the highest one. And p square does not divide I0. This is a criterion. Then, if there exists such a prime, then f of x is irreducible in q of x. It's quite complicated to look at all these conditions, but it's a very useful thing that is very famous in algebra. So we have done that. We have proved it. That was Eisenstein. It's a technical thing. But it's used quite a lot. And then a more conceptual thing was this theorem 425, which is an idea that is used a lot in many contexts in algebra, that if you have a problem, in general, you try to look at the problem mod p for prime numbers p. So 425 is the following. You have polynomial f of x being ak x to the k plus a0 ai integers. And then you pick a prime, p prime. You are not allowed to let p be a divisor of the highest coefficient, because then if you do that, then you reduce the polynomial to polynomial of smaller degree. So you're not allowed to have a polynomial that factors into the highest coefficient. In that case, you reduce the polynomial, you produce a polynomial f bar of x being ak mod p x to the k, and then you consider it like this, plus a0 mod p. You take all the coefficients and mod by p, and if you have this, then this is non-zero, so you are left with a polynomial of the same degree. You have this reduced polynomial where you have a reduced mod p everything. And then the result is the following, that if f bar of x is irreducible, in ZP of X, then the original one, F, is irreducible in Q of X. So that's an idea that is quite common and quite useful, that you look for mod P, and once you have modded with P, then you have a finite number of cases to investigate. So this has only a finite possible number of roots. You can check it by finite computation. If this is irreducible, then the original polynomial is irreducible. But we have to be a bit careful, because what does it mean to be irreducible? It's not that it has no roots. If it's reducible, then if it has roots, then it's reducible. That's true. But if it has no roots, it doesn't need to be irreducible. So roots and irreducibility. F has a root. Alpha implies that f of x is some g of x times x minus alpha. So that's reducible. If f of x has degree 3 or less, less than or equal to 3, then no root implies that it has no linear factor, and therefore it's irreducible. So if it has no root and it's of degree 3 or less, then it has no linear factor, so the only factor is of degree 3, so it's irreducible. Irreducible. But if the degree of f is 4, then you have to check more carefully. So, for instance, you could have yeah, let's say in if you have a polynomial f of x in R of x, you could have a degree 4 polynomial of the form f of x equals x squared plus 1 times x squared plus 1. The two factors have no roots in R, because the roots are the imaginary numbers. This is a 4th degree polynomial. Oops. It's a 4th degree polynomial, and it has it has no roots, but it's reducible. So for higher degree polynomials than 3, you have to be more careful when you check that something should be irreducible. Yeah, we are running out of time. What should we do now? Let's see. We have done about half of things. I don't know if you're really inspired to meet again, or if we just should. How do you want to prepare? The exam is on Tuesday next week, is it? So how do you want to work the last week? Do you really want to meet once more, or do you just say that I can be available for that sometimes for questions and so on? I think that's better. Let's see my schedule for this week. April, May 18. Yeah, I got a bit of time tomorrow and the day after tomorrow. Then there's an exam in 228, and an exam on Friday. So towards the end of the week, I'm quite busy with exams.
Can I ask,
Yeah.
if we had had more time today, what would we have done for the rest? Would we have gone through the last part?
I would have been going through the last parts. I wanted to say something about the last chapters. I mean, what we really want to. I wanted to say something about what is important in the later chapters.
Could you write it for us,
I
maybe?
can write it for you, or do a recording of something of this. I can do that. Perhaps that's the best solution. I think I do that. I do a recording that I make with a summary of the rest of this. Yes, I think that's the best. Yes, and I post it. I will be able to post it on Wednesday, I think. Yes. But if you have questions, you have to send me mails, or we could arrange some kind of. Did you have a need for some kind of online question hour sometimes? No. So you just mail me if you have questions about the contents of the course. Yes.
I just wanted to have precision about how much we need to know about field extensions, because it is a subject that is really present in all exams.
Yes, exactly. How much do you need to know about field extensions? I say that you need to know less about the field extensions than what you see in the old exams. Because in the old exams, you have questions like, what is the dimension of this extension generated by two elements and these kind of things. I'm not going to ask these kind of things. But you must know about field extension, the fact that the idea of a single extension is that you start by a polynomial that is irreducible, and then you extend it by taking this construction where you do f of x divide out by the polynomial, and then you get a single extension containing one root of these kind of things you need to know. But these kind of more subtle things about there's separable extensions, and there are these generated by several elements. I think short answer is that we are only going to look at single extensions by a single element. Yeah. We're not doing any of these more subtle things. And why did I not do it? Because I wanted to discuss other things, and all these subtle things about separable extensions and normal extensions and so on. All that is geared up to understanding the Galois theory in chapter 12. As long as we are not have time to do Galois theory, then I don't see the reason to go deeply into all these special things of these extensions. Galois theory is quite fascinating now. I start to understand it, so it's quite fun, but it takes a bit too much time for us. Okay. I'll make a recording of the last chapter and what I consider to be important there. I'm sure I'm going to do it more structured than I was today, because today was 18th of May. Good. So that will be posted on Wednesday. Ha det bra, Elisabeth.